And we need to take one more pass at that in-sample, between-sample variance thing. So if we take our samples close to each other, then we would be minimizing in-sample variance and maximizing between-sample variance. What we're really looking at then is the difference between short-term variance and medium-term variance. There are some places where taking a bunch of samples close together makes sense. Say, for example, we were looking at code metrics across a system all at the same time. Or we had 6 production lines that were all producing things, and we were going to take 6 samples, one across each of the production lines at the same time. However, if you take this to an extreme, the sample variance becomes a bad estimator for process variance. If we take all of our samples right next to each other, then our average range is going to become really small. Our charts are going to be overly sensitive because we will have put all of our variance into between sample variance instead of capturing it in the in-sample variance. So stop and think about what we're talking about here. If we're going to gather our samples all close together and then wait a while and then do it again, think about what portions of the variance we're capturing within the sample and what portions of the variance we're leaving between the samples. Essentially, we've made the in-sample variance, that short-term variance, so small that most of the common cause variation is going to be left in the between-sample variation. That means that the between-sample variation is going to have a pretty significant random effect, and as a result, our control limits will be close to each other, the warning limits and action limits will both be close to each other, and everything will look out of control because there is a random effect in the between-sample variance. Now I'm confused, because we said we wanted to minimize in-sample variation and maximize between-sample variation, but that's really only true to a point. What we really want to do is we want to capture all of the common cause variation in the sample variance, because that'll make the control limits just perfect. And then we want to capture all of the assignable cause variation in the between-sample variance, because that's how we'll detect it. There's one other problem that we run into when we gather our samples too close to each other. All of the statistical techniques that we're using are assuming that our samples are IID, independent and identically distributed. So the trouble is, when you take the samples really close together, there's a chance that they may not be independent. If they're coming off the line at the same time, that may mean that the second was affected by the first one, or that they're all affected by the particular humidity at that moment. And if we're using the example of running tested features the way software engineers would, a really productive day might be followed by a day that's designed for the next set or some refactoring from the last set. And so what you do on one day may affect how much you get done on the next day. So there are times when you don't have a choice, when you have to sample things that are closely in time and therefore may not be independent. And the question is, what do we do in that situation? So the real problem is that the average range is not a good estimator of the random variation in the process. So we need some other way to estimate variation. So one strategy is to estimate the standard error from the means instead of from the ranges. And that looks an awful lot like the way you calculate variance normally. So if you're worried that you might be gathering things too closely in time, the thing to do is to calculate both of the ways of estimating standard error. And if they're close, then use the one that's based on the average range. But if they are not close, then use the estimator that is calculated from the means. And then your action lines are plus or minus 3 sigma away, and your warning lines are plus or minus 2 sigma away.